You might think they're very different from each other. The Big Bang is very, very dense and very, very hot, while the remote future will be very, very rarefied and very, very cold. The once unquestionable Big Bang theory is now under the relentless scrutiny of legendary physicist Roger Penrose. The latest discovery hints that the universe might be hiding secrets that will shake the very foundation of our cosmic origins. Forget everything you thought you knew about the Big Bang theory and brace yourself. Penrose's theory suggests that the Big Bang might not be how our universe came into existence. Is the Big Bang really just a chapter in the story of our cosmic origin? If yes, what alternative theories explain the beginning of our universe? Join us as we delve into the words of Roger Penrose. We detected a hint of the previous universe that existed before the Big Bang. The prevailing theory in science and astrology is that more than 13.8 billion years ago, the universe was in an intensely hot and dense state known as the Big Bang. However, recent imagery captured by the James Webb Space Telescope, JWST, challenges this popular scientific understanding. While these images may captivate the general audience, they are causing ripples of concern within the cosmological and astronomical communities. Experts are surprised by the differences these images introduce to the long-established Big Bang theory. This newfound data has triggered significant unrest in the scientific community, leading astronomers such as Alison Kirkpatrick from the University of Kansas to re-evaluate the validity of their prior research. The focal point of the unrest is the characteristics of the galaxies portrayed in the JWST images. Contrary to scientists' expectations of the Big Bang theory, these galaxies appear unusually small, smooth, and remarkably old. According to the theory, as space expands, galaxies and other celestial objects should appear bigger as they move away from us due to the stretching of light. However, the JWST images reveal a confounding phenomenon where galaxies seem to reduce in size as the distance increases. Even galaxies with greater mass and brightness than our Milky Way seem 2 to 3 times smaller in the JWST images compared to previous observations by the Hubble Space Telescope. Moreover, the observed redshifts in these galaxies are 2 to 3 times more pronounced, further questioning the assumptions of an expanding universe in the Big Bang theory. These observations imply that distant galaxies must be tiny to account for this optical illusion, which appears implausible. These tiny and smooth galaxies undermine the notion of expansion, casting doubt on the validity of the Big Bang theory. Initially, proponents of the Big Bang theory recognized that their assumptions required the existence of small and dense galaxies, informally known as Mighty Mouse galaxies, based on earlier observations from the Hubble Space Telescope. However, the situation has been further complicated by JWST images, which question whether these compact galaxies could transform into larger ones through collisions or expansion. The JWST images portray well-defined spiral structures and smooth disks resembling galaxies observed in the present day. This contradicts the anticipation of rough and distorted galaxies resulting from collisions. Without significant mergers, these minute galaxies cannot grow 100 times larger, thus challenging the concept that they were initially small. This revelation disputes the optical illusion predicted by the expanding universe theory, suggesting a potential absence of expansion, and no Big Bang. The age and abundance of galaxies in the JWST images present further challenges for the Big Bang theory. By using infrared filters, the JWST captures the colors of distant galaxies, allowing astronomers to estimate the age of the stars within them. According to the theory, these galaxies should represent approximately 400 to 500 million years after the Big Bang. However, some of these galaxies exhibit stellar populations over 1 billion years old, contradicting the assumption that nothing could have existed before the Big Bang. Furthermore, theorists expected that as the JWST delved deeper into space and farther back in time, there would be fewer galaxies and eventually none during the Dark Ages. However, the images reveal galaxies as large as the Milky Way even just a few hundred million years after the theorized Big Bang. Additionally, the number of galaxies observed at redshifts above 10 is at least 100,000 times greater than predicted by theorists. The formation of so many substantial galaxies in such a condensed time frame challenges the Big Bang theory. These discoveries have also sparked a re-examination of the concept of time. Some scientists propose that time is merely a human construct, serving as a tool to distinguish between the present and our perception of the past. They posit that time is an illusion created by human memories, suggesting that all events, past and future, happen simultaneously. This perspective challenges the traditional notion that time progresses strictly in a forward direction. Certain proponents of the Big Crunch theory go even further, suggesting that time may reverse if the universe stops expanding and begins contracting. This reversal could result in an undoing of the cooling and expansion observed in the Big Bang, ultimately leading the universe to collapse back to its point of origin. The consequences of what follows a big crunch remain uncertain, but there are various theories. Some propose a fresh start with another Big Bang, while others suggest the possibility of the universe simply ceasing to exist. Some ideas entertain a cyclical nature, repetitively creating multiple universes. The ongoing debate about the direction of time has prompted scientists to question its fundamental nature. Some advocate for a block universe concept wherein space and time are intricately interconnected in what is known as spacetime. Drawing from Albert Einstein's theory of relativity, the block universe viewpoint asserts that time and space form part of a four-dimensional structure where each event has its position in spacetime. This implies that past, present, and future coexist in spacetime, making them equally significant. Physicist Max Tegmark from the Massachusetts Institute of Technology seeks to address this concept by suggesting that reality can be depicted as either a three-dimensional space where events unfold over time or a four-dimensional space where nothing changes. If the latter is true, it implies that everything already exists at any given moment, encompassing the past, present, and future. However, the illusion that the past has occurred and the future is yet to come leads us to perceive change. Julian Barber, a British physicist renowned for his extensive writings on time, provides a unique perspective. He likens our experiences to a series of nows, emphasizing that our awareness is limited to our brain state. According to Barber, the perception of the past arises from storing memories in our brains. Drawing from the spacetime theory, Barber introduces the concept of Platonia, where each point represents a now. He suggests that what we commonly perceive as the past is an illusion crafted by our brains. This discussion circles back to Albert Einstein's theory of spacetime, which has stirred confusion in the field of physics. Scientists are now contemplating the potential consequences if Einstein's theory were proven incorrect. Could discarding the spacetime theory lead to a better understanding of the universe? Such a development would mark a significant milestone. Throughout history, scientific revolutions have been pivotal for progress. Dissatisfaction and doubts often pave the way for new theories to replace old ones, a pattern witnessed in astronomy and physics. In the early days, humanity believed that Earth was at the center of the solar system, a notion that persisted for over a millennia. However, Nicholas Copernicus proposed a heliocentric model, suggesting that Earth is another planet orbiting the Sun. Despite initial resistance, this model gained support with the advent of telescopes. Isaac Newton further contributed to our understanding by explaining that the Sun's gravitational force causes planets to orbit it. Newton's theory dominated scientific thought for nearly 300 years until Albert Einstein introduced his general theory of relativity in 1915. This new theory effectively explained the quirks in Mercury's orbit and received strong confirmation during a 1919 solar eclipse near Africa. Unlike Newton's idea of gravity as a force, Einstein saw gravity as a result of space bending. He suggested that everything in the universe exists in a four-dimensional structure called spacetime, and big things like the Sun make this structure curve. This curve affects how planets move, and observers see it as a pull similar to Newton's description. Einstein's spacetime theory has been the dominant idea for over a century, even more so after the discovery of gravitational waves in 2015. However, like previous theories, it might face challenges as it clashes with quantum theory, another significant physics theory. The quantum world is known for its strange features, where particles can be in multiple places simultaneously. In the 1930s, Schrödinger illustrated the oddness of quantum superposition with his famous Schrödinger's cat experiment. In it, a sealed box has poison connected to a hammer triggered by a quantum measurement. According to quantum physics, until someone checks, the particle is in both states, making the cat both alive and dead. But this quantum idea doesn't match the smooth spacetime fabric. Even Sabine Hossenfelder, a theoretical physicist at the Frankfurt Institute for Advanced Studies, admits this conflict. According to Einstein's spacetime theory, a gravitational field can't be in two places simultaneously. The theory follows matter and energy subject to curvature. On the other hand, quantum physics suggests that matter and energy can simultaneously be in many states, challenging traditional locality ideas. This raises the question of where the gravitational field exists. Hossenfelder concedes that there is no satisfactory answer to this question, underscoring the ongoing challenge of reconciling general relativity with quantum theory. Attempts to merge these two theories result in mathematical inconsistencies, with calculations sometimes yielding probabilities greater than 1 or even infinity, lacking meaningful physical interpretations. Consequently, the two theories are deemed mathematically incompatible. Like historical monarchs seeking alliances, physicists are now searching for a unified theory of quantum gravity. This endeavor aims to reconcile and establish harmony between the two rival theories. String theory is a prominent proposal in this quest, often considered an unconventional possibility. String theory posits that all matter consists of minuscule vibrating strings, presenting an intriguing solution to the conflict. However, this theory introduces additional dimensions beyond the 4 dimensions of spacetime, dimensions inaccessible to humans. These extra dimensions make it challenging for scientists to experimentally verify string theory, as current technology cannot access them. The discovery of a quantum gravity theory could significantly reshape our understanding of the universe by uniting these two rival theories. It has the potential to replace the Big Bang theory. Roger Penrose, a renowned physicist, introduces the concept of conformal cyclic cosmology (CCC), which asserts that the universe undergoes an infinite cycle of deaths and rebirths. Penrose speculates that every cycle concludes with the complete consumption of all black holes, resulting in the evaporation of their constituent particles into photons. Since photons lack mass, they can navigate vast distances across the expanding universe without resistance. This absence of mass could lead to the disappearance of time, transforming the universe into a dense, homogeneous sphere, a state akin to the Big Bang. Penrose proposes that traces of these previous cycles can be found in cosmic background radiation, the faint glow of microwaves permeating the universe. He observes unexplained anomalies in the cosmic background radiation map, referred to as Hawking points. Penrose suggests that these points might represent energy remnants from ancient black holes, offering evidence of past cycles. The term Hawking points honors physicist Stephen Hawking, who hypothesized that black holes emit radiation when they evaporate. By analyzing these Hawking points, scientists could gather crucial evidence supporting Penrose's theory. Penrose firmly believes that his conformal cyclic cosmology theory provides a more plausible explanation of the universe's origin than the Big Bang theory. He posits that the Big Bang marked the culmination of a prior cycle rather than the universe's inception. However, CCC has encountered skepticism from other experts, with researchers questioning the authenticity of the Hawking points. Some critics argue that the observed hot regions might be noise in the background radiation map rather than remnants of prior cycles. Currently, there is no experimental evidence supporting the existence of these extra dimensions. While intriguing mathematically, string theory's accuracy in describing our lived spacetime remains uncertain without experimental validation. In response to perceived shortcomings of string theory, physicists have turned to an alternative approach known as loop quantum gravity, LQG. LQG reconciles the two theories by challenging one of the basic principles of general relativity, which asserts that spacetime is a continuous, smooth fabric. Instead, LQG proposes that spacetime consists of interwoven loops, providing structure at the smallest scale. This can be compared to a length of cloth that appears smooth initially but reveals a network of stitches upon closer inspection. Alternatively, it resembles a photograph on a computer screen composed of individual. The challenge with loop quantum gravity arises from the incredibly tiny scale that physicists refer to as small. These potential flaws in spacetime would only be detectable at the Planck scale, roughly a trillionth of 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 a meter. Jane Maluko at the University of Nottingham points out that the number of loops in a cubic centimeter of space at this scale would surpass the total number of cubic centimeters in the entire observable universe. Testing LQG at the Planck scale presents a formidable task. It would require a particle accelerator about 1 trillion times more powerful than the Large Hadron Collider at CERN. That's not all. Such a colossal device would also need to be as vast as our Milky Way galaxy. Nevertheless, a group of physicists from the UK, France, and Hong Kong are working to propose an alternative method soon. They plan to use an ultra-cold gas containing billions of cesium atoms in a state known as a Bose-Einstein condensate to explore whether gravity shows quantum properties. The universe itself provides another avenue to investigate small spacetime defects. Light from distant parts of the universe has traveled through billions of light-years of spacetime. Although the effect of each spacetime defect may be tiny, interactions with multiple defects could accumulate. As such, it could lead to observable effects over vast distances. Astronomers have examined light from distant gamma-ray bursts for over a decade to find evidence supporting LQG. These cosmic events occur when massive stars collapse at the end of their lives. However, there are unexplained systematic distortions in the spectrum of these distant bursts, as observed by Hassenfelder. It remains uncertain whether these distortions occur during their journey or are related to the bursts themselves. Due to this uncertainty, Progress may require moving beyond Einstein's idea that spacetime is a smooth and continuous fabric. Einstein proposed that spacetime is like a stage, always existing, and objects move within it even without celestial bodies. However, physicists Laurent Friedel, Robert Lee, and George Emilino Camiglia present a different view. They argue that spacetime isn't independent of objects but is defined by their interactions. In their perspective, spacetime is a product of the quantum world, not something separate from it. This idea challenges the norm, but Emilino Camiglia considers it a precise solution to a long-standing problem about locality and a quantum phenomenon called entanglement. The appeal of the modular spacetime theory lies in its potential to tackle issues in theoretical physics and explain strange quantum behaviors physicists often observe. Entanglement, where changing the properties of one particle instantly affects another particle even if they are far apart, is one such phenomenon. Einstein called this spooky action at a distance. The modular spacetime theory accommodates such behavior by redefining the concept of separation. If spacetime emerges from the quantum world, proximity in a quantum sense becomes more fundamental than physical proximity. Emilino Camiglia explains that different observers may have different ideas of locality depending on the context, similar to how we feel closer to a loved one far away than a nearby stranger. Hassenfelder adds that these non-local connections are acceptable as long as they remain relatively small. Friedel, Lee, and Emilino Camiglia have been developing their idea for the past 5 years, taking a conservative approach step by step. Despite the gradual progress, Emilino Camiglia acknowledges the exciting nature of their research, considering it both compelling and promising. The team's unique approach centers on exploring a quantum world influenced by gravity rather than quantizing gravity itself as seen in loop quantum gravity. Like any scientific theory, it needs testing, and the team is currently working on incorporating it into their model. While this might seem abstract and relevant only to academics, it has the potential to impact our daily lives significantly. Our existence is closely connected to space and time, and any shifts in our understanding of spacetime would affect how we understand gravity and quantum theory. This plays a crucial role in the functioning of our current devices. Sabine Hassenfelder points out that a better understanding of the quantum structure of spacetime could have implications for future technologies. Though these effects may not be immediate, they could become apparent within the next 200 years. Hassenfelder uses the metaphor of a monarch at the end of their reign and a new successor being overdue. Once we identify the most likely contender among various theories, a revolution in theoretical physics could occur. Astronomers, scientists, and physicists are confronted with this situation and must consider the best course of action to address these ideas and discoveries. In addition to string theory and loop quantum gravity, several other theoretical frameworks and ideas have been proposed to unravel the mysteries of spacetime and gravity. These alternatives seek to provide new perspectives on the fundamental nature of the universe. These theories include causal dynamical triangulation (CDT), emergent gravity, asymptotic safety, quantum graphity, and non-commutative geometry. Causal dynamical triangulation (CDT) is a quantum gravity approach that views spacetime as a network of triangles. This theory aims to describe the emergence of space and time through discrete building blocks, focusing on the causal structure of events within spacetime. Emergent gravity challenges the traditional idea of gravity as a fundamental force. It suggests that gravity is not a fundamental force but emerges as an effective description of more basic quantum interactions. The holographic principle, inspired by string theory, is an example where a lower-dimensional theory accurately represents a higher-dimensional spacetime. Asymptotic safety challenges the conventional idea that gravity becomes uncontrollable at high energies, proposing that it remains well-defined and predictable even at extreme scales. Quantum graphity envisions spacetime as a dynamic graph with nodes and edges interacting to produce familiar space and time properties. Non-commutative geometry challenges the idea that spacetime coordinates commute at small scales. It proposes non-commutative properties that could fundamentally change our understanding of the universe. While string theory and loop quantum gravity are prominent contenders in the quest for a unified theory, scientists have diverse perspectives on spacetime and gravity. Two notable figures with contrasting viewpoints are Roger Penrose and Michio Kaku. Renowned physicist and mathematician Roger Penrose has greatly helped us understand general relativity and black holes. His idea, called conformal cyclic cosmology, suggests that the universe goes through endless cycles of expanding from a Big Bang to contracting in a Big Crunch. Penrose also explained how black holes form through gravitational collapse, giving us insights into these celestial objects. On the other hand, Michio Kaku has been instrumental in developing and popularizing string theory. Despite acknowledging its importance, Kaku recognizes that string theory needs experimental proof. He emphasizes the need for better technology, like more powerful particle accelerators, to test the predictions of string theory. Kaku is open to alternative ideas, including loop quantum gravity and emergent gravity, hoping they can provide new insights into spacetime and gravity. The scientific community thrives on sharing ideas and exploring various theories. As researchers delve into the universe's mysteries, debates persist on the most promising approach to unify general relativity and quantum mechanics. Each scientist contributes unique expertise, fostering a lively theoretical physics landscape and paving the way for future breakthroughs.